Hello, we're going to talk about waves today. We're going to start looking at this with water waves, but learn that waves can be kind of in any medium, any type of material. But we're going to start with water first. So we have our water wave, right? And then we have this line here, this dashed line that kind of like cuts through the middle. And that is what we call the still water level, or like if the wave wasn't there, this is where the water would sit. Um, and so here we have some features of the wave. We have the crest, which is the peak, the highest point that the wave gets to. And then we have a trough, which is the lowest point the wave gets to. So the crest is above that still water level line, and the trough is below. And the waves have multiple peaks and troughs. As you can see just in this image, these are all crests or peaks. And then we also have three troughs too. And then the height of the wave is the distance between the crest and the trough. Um, yeah, so let's look at some more features. There's also the amplitude, and it's a little hard to tell what this is indicating, but the amplitude is how tall the wave is, like how far away it gets from that still water level. So the distance from the crest or the trough to the center of the wave line. So distance from here to the center line or from here to the center line. Then there's the wavelength, and that's the distance between any successive identical parts of a wave. Um, and how a wave works is it's just the kind of same um, shape or whatever continuing on. So we have one wavelength is just from one of the same part of the wave to the next. So we have one peak to one peak, that's a wavelength, and wavelength being length, it's in distance. But you could also say from trough to trough is a wavelength. And from like this like middle point of the wave to the same middle point of the next one, that's also a wavelength. So all of those should have the same value, but you can just measure it from different spots. There's also the frequency and the period. So frequency can like explaining it in this way might make it sound a little bit weird, but it also relates to other stuff. So I think later on it'll be easier to kind of understand. But the idea is that the frequency is the number of wave crests that pass from point A or point B each second. So it's kind of like how fast the wave is traveling, sort of like how many peaks or how many crests you get in a second. Like if you're just looking at point A, how many times does it give us another crest? That would tell us the frequency. So if it's really slow, if we get like one crest a second, that's a low frequency. But if it's really fast, we have like several crests within a second or whatever our time interval is that we're looking at, that would mean it's a higher frequency. And then the period is just the time it takes for a wave crest to go from point A to point B. Or you can also think of it as just instead of the wavelength being length, period is the time it takes instead of the distance traveled. So again, it's just any consecutive spots in the wave that are like identical. So you can go from the trough to the trough, from the crest to the crest, or again, from like where it's going up here to where it's going up there. All of those should have the same distance, physical distance between them, and take the same time to travel that distance. Additional thing about the frequency, which makes it, I think, a little bit easier to like determine because it's easier to find, potentially easier to find the period depending on like what information you have. And then you can use the period to find the frequency. So this is how they relate. The frequency is just one divided by the period, or the period is one divided by the frequency. And period is in seconds, it's time. And then frequency is in one divided by seconds, which is called hertz. So that's just how those two relate to each other. And we'll spend more time with these. So it's okay if that's not entirely clear yet. So let's look at this little clip here. The idea we're trying to convey here is that the waves move through the medium, which is water here, and in our little like simulation clip. Um, and the individual water molecules move up and down in their general position, but the wave just carries through. So if we look at like the yellow points, those are, well, actually all the dots are meant to indicate water molecules, but we can really see the path of these yellow ones. And we can see that as the wave itself moves through, the water molecule kind of goes in a circle, or it does go in a circle. So the wave just moves through. The water molecules don't all follow the wave. They do move around due to the wave traveling through. But the wave itself is like separate from the material it's traveling through. Another example of waves outside of water, like I said, they work in lots of different materials. So you can send a wave through a rope or a string. We have an example here where one end is attached to a wall. That's what's happening here, a wall. And then this person is shaking the rope up and down. And you can tell just like from the arrows, they're saying like, okay, first they pulled it up and then they pulled it down. And if they keep shaking the rope like that, we'll just end up with this kind of continuous wave through the rope. But if they stop, we'll actually be able to see the wave itself, like this part of it, travel down the rope. And that's sending the wave through the rope without changing the rope, just like we're sending a wave through the water without changing or really displacing the water very much. There's two types of waves, and also here's another example of waves in a different material or object. This time it's in slinkies. So longitudinal waves, longitudinal waves are where parts of the medium that the wave is moving through move back and forth in the same plane as the wave, or like the same sort of direction, or like in this example, the wave is moving horizontally, and so are the parts of the material, the slinky. So they push the slinky back and forth, and that sends a wave through the slinky. And that is a longitudinal wave when you are moving the wave back and forth, and how the wave is generated is also that sort of back and forth motion. Transverse waves are when parts of the medium are in a plane perpendicular to the motion of the wave. So the wave is horizontal back and forth, but we're moving the slinky up and down instead. So longitudinal means you're moving the wave in the same plane that the wave itself moves. And this transverse is when they're perpendicular. You can also find the speed of a wave just based on its frequency and its wavelength. So remember, wavelength is distance, and then frequency is 1 divided by time, 1 divided by seconds. So if we multiply the frequency by the wavelength, that's distance divided by time. That is a unit of speed. So here's an example that the wavelength is 1 meter. And I am telling you that, that we have determined somehow that the frequency is 1 hertz or 1 hertz. No, I don't know. Ignore the plural of the unit. It's okay either way. So 1 meter times 1 hertz equals 1 meter per second. So that's our wave speed. So if you know the frequency and the wavelength, you can get the wave speed. Or also if you know the period and the wavelength, you can get the wave speed because you can get the frequency from the period. I also wanted to have us look at these waves from another perspective, also because you're going to have an activity where you work with this. So this is like waves in water from above. So this is a simulation where you like drop water from this spigot, and it sends out waves. And so instead of looking from the side like we were before, we're looking from above. And I just want to show that like this is the view from the side, like from this simulation. This is the side view. And you can see that that is still that wave pattern we saw. So this, I just want to indicate like different ways of representing the same thing so that when you're looking at like different versions, you know how to kind of translate them in your head. These wave patterns here, so again, we're looking at sort of above view, are showing wave interference. So what happens is we have two wave sources near each other. And as the waves travel out from their source, the wave fronts, which is just kind of like the start of the wave, the crests and troughs interfere with each other when they come together. And so you can see this when you have darker and lighter regions. So because the waves are interfering. So we have like these bright spots where the waves are meeting, and that is interference. And then we have these dark spots where we also have some interference happening. And you can see it here too. We have like these bright spots and then the like darker spots. But what is happening? Like, why does that happen? So let's take a look at this. It's because we have two waves interacting, like arriving at the same point at the same time. And when that happens, they interfere, meaning they combine either constructively, when two crests meet in phase with each other. So they both arrive at a point looking like this. We get constructive interference, and that results in those bright spots or like a bigger wave. And then if they are out of phase, where the trough and a peak meet instead of the peaks and the troughs meeting, you get destructive interference where the wave cancels out instead. So you can see this here. We have destructive interference for these dark spots, and then constructive interference for these light spots. And now we're gonna kind of work a couple of examples of interference. One moment. Okay, now we have to use our imaginations a little bit first and imagine that we have two waves in a string, and they're going to pass each other within that string. Okay, so right now, how we've drawn them, that's just like two separate waves, right? But they're part of the same medium. They're going through a string. So they don't actually look like this when they start to overlap. And we can figure out what they look like, what the interference looks like in this way. So we have our waves, okay? But then I'm going to look at another version of it, and I'm going to draw dots where the combined wave would be, okay? Because remember, this is the 0 point. So first, it's just there's nothing of the lower wave here. So those are going to be in the same spot. And then this part of the lower wave is at 0. So it's still going to be the upper wave that dominates there. Okay. And we'll do it from the other side too. So same thing. Those first 3 spots are the same wave. They're the original wave. But then if we look at this point, here, yeah, this kind of part here, they're overlapping, right? And we can see that the upper wave goes like kind of 1 square up, and the lower wave goes 1 square down at that position, right? So those are going to cancel out actually right there. So let's draw a dot right here. It's at 0 at that point. But then what about in between? So kind of here-ish, it looks like this one has, you know, 1 little triangle, and this one has a square and a triangle. So we're going to have this part cancel that part. So we end up sort of somewhere in the middle. We end up sort of like there-ish. That could be slightly off, but close. And then the same thing happens on the other side. And then I'm going to quickly redraw my dots for you, and we'll just connect it all. Let's see, we were like right here, here, here. Yeah, there we go. And then we connect our dots. We do our best. So the blue now is showing us the wave once they're combined, right? And so this is showing us an example where there is interference, constructive and destructive, right? It's not fully destructive. But that's what's happening in the middle here is because some of our wave, these are meeting at the wrong spots, right? So they end up canceling each other out. Let's try another one, maybe easier, maybe not, where we have, let's draw like their wave velocity indicators. So they're coming toward each other again. But these are both up, right? So they're going to combine constructively instead of destructively. So let's draw our dots again. So those parts are still the same with how we're overlapping, right? Like this wave is at 0 when that one's at that spot. So like that doesn't cancel it out, same as here. But then we're at a spot where we're starting to overlap, right? So you can kind of think of this multiple ways. You could just say, okay, we just have like this extra triangle right here, right? Just kind of like two of this triangle. So we could just put it up here, and that would be that. You could also look and say, actually, I think that's kind of the ideal way to do it. So then our dot, oops, just comes right there. And then let's do our dots on this one again, which, sorry, I should have already had the dots on these third ones. That's okay. So we end up with like this flat top version, right? So that's our constructive interference. We have this part right here where our waves overlap and where normally that wouldn't be anything, like our waves just this little triangle shape. There wouldn't be anything there, but they overlap, so we add them up. And then the last example of these, again, they're overlapping. Now they're just overlapping at a different point. Okay. So again, these parts are all the same because there's no overlapping happening there. And then right here and here, it's another time where like the other wave is at 0. So the only difference here is the double triangle, just like in that previous example, right? Oh, I didn't mean to put the blue dot there. But this double triangle, right? So we can just fill in this empty space we have. And this is what our wave, combined wave looks like. Here, here, here. And then connect our dots. And we have another example where it's like a flat spot in the middle, but then the rest of our waves on the outside. Okay, so this is what happens like when we zoom out and see these different examples. Is we have our waves and we look at, how they overlap with each other, and then we can draw what the overall wave looks like. And we can do that a less like kind of intricate way in this example. Like this one is just going to be try our best to draw. So we have these two waves for A. We have these two waves approaching each other. They're going to meet here in the middle, and they're both above the 0. So they're going to combine into something even bigger. Maybe not quite that big, but that's okay. We're just estimating here something like that. It might be a little off, but close enough. And then let's look at B. So we just have two smaller waves, right, that are going to meet here in the middle. So those will probably combine into a wave that looks like this one, right? So let's try that. kind of like that. Okay. And then we have C, where we have waves that are going to destructively interfere, right? So these are going to meet up right here, but they're the same size, right? So those are just going to cancel out. So we just actually, oops, I already had that. We just get a flat line right there where they meet. That one's easy. And then this one, we have some destructive interference here too, but we have a bigger wave on the bottom and a smaller wave on the top. So we're just going to subtract this much from the lower wave. So really, we'll just end up with like the smaller wave upside down, like this. Okay, I hope that makes sense. I know it could be a little confusing. I kind of wanted to introduce these ideas before I give you an activity with them, but we might have to come back to them, and that's okay. Actually, I think this demonstration will make it a little clearer what we were doing. Maybe I have these things going on in the wrong order, but that's okay. So we have, this is the equivalent of a wave on a string, okay? And it's fixed at one end, and then we have this little pulse machine at the other end, so we can send a wave pulse like that. And we can see how it goes through the wave, and then when it hits the bracket at that fixed end, it reflects. So it bounces back, but it goes upside down, right? It like does the opposite. So we can send, I'm gonna put it in slow motion, and we're gonna send another wave pulse through of the same kind, and then we'll watch what happens when those waves overlap. So see, you can see some of those shapes that we drew with the triangles, right? Like, let me see if I can follow. Right there. Hey, perfect. So that is that first shape we made, right? Or I did. And that's just because we had two triangle waves going along the string and running into each other. And because of what the wave was doing, when the two different waves run into each other, with this one, we get destructive interference, right? I think there should even be a spot where they're like flat, but it's going to be really quick, I think. See there, just like a split second for them to be flat. We can also try to, let's restart and let's see if we can combine the waves positively. Sorry, I'm thinking about how I could do that. I don't think I can with this, actually, now that I'm thinking about it. I mean, let's give it a shot. Oh, no. That's two waves really quickly in a row. That's not right. Let's try this again. I can go at normal speed. And we do like that. No, because they're always going to destructively combine in this. But you could imagine that constructively it would just be bigger, right? Just like meet up in a slightly different way. Okay, now we have the concept of standing waves. So this is what happens when you send a pulse with a specific frequency that's like specific to the wave material itself, like the string or whatever. I guess this is the string. And it looks like the wave just stands still. But what's happening is like what we saw, it's bouncing off and reflecting. But it's at such a frequency that it really just looks like, okay, we just have kind of one wave bouncing up and down. And I'll show you a video of this in a moment, but I want to talk a little bit about standing waves first. Oops. So yeah, here's what it looks like. The incident wave, which is just like the initial wave you send, and the reflected wave, which is the one that bounces off the fixed end, are in phase with each other, which means their peaks are in the same spot and their troughs are in the same spot. So we just kind of look like it's bouncing up and down, or even just like the wave is just standing there, hence the name standing wave. And then there's a null or node point, and that's just like in the middle where it's at 0. Another example would be where they're out of phase, where the trough of one is the peak of the other, and so on. And so we actually just end up with a flat again, like we were looking at. And this is just showing them in phase, but like the other direction. And then this, a combination of the times where they're in phase, is the standing wave, where it's just like bouncing up and down, back and forth. And here, I will show you what that looks like. Okay, so we have this physics professor and his helpful assistant. Oops, one second. Okay, sorry, the little green screen thing wasn't showing me. Anyway, so he's going to send a wave through the string and see, or it's a slinky. And we can see here, this is a standing wave, right? It just looks like it's bouncing up and down, but what's really happening is one wave is being sent and then it's reflecting and going the other way, and it just happens to be in phase. And so we get this pattern, and this is a standing wave. And part of the reason why you're seeing a video of some random professor and not me is because I haven't ever tried to do this myself. Maybe I will try, but yeah, I don't have a recording of it. But anyway, that's pretty cool. And actually, that's all I have for you. So that is our intro to waves. Have a great day.